Now let us solve some MCQs which are based on nature of chemical bond. Question number 1 is how many bonds are there in the molecule given. If you look at this particular molecule, it is a benzene ring with the side chain. Now whenever you have this benzene ring, we should not forget that each carbon is bonded to certain hydrogen. And since this is terminal, it is bonded to 3 hydrogen. So in this case, if I have to calculate the sigma and pi bonds, all single bonds are called as sigma bonds. Now in the double bond, there is one sigma and there is one pi bond. So overall in this case, we'll find 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. There are 19 sigma bonds and we can see 1, 2, 3, 4. There are 4 pi electrons, hence our option is C. Question number 2 is which statement is not correct related to option A, a sigma bond is weaker than the pi bond. Option B, a sigma bond is stronger than the pi bond. Option C, a double bond is stronger than the sigma bond and a double bond is shorter than the sigma bond. Whenever I talk about the sigma bond, it is something the overlapping of the orbital along one axis. Since they are overlapping along the same axis, the actual overlap is considered as a stronger. But when I talk about a pi bond, it's a lateral overlap. And the lateral overlap, the overlapping is considered as a weaker. So when I talk about sigma and the pi bond, definitely the sigma bond is stronger than the pi bond. But in the option A, it has been written as a sigma bond is weaker than the pi bond. Hence the not correct statement is option A. Question number 3 is we have to find the enolic form of the acetone. Acetone is CH3, C double bond O, CH3. When it undergoes the tautomerism, one of the hydrogen from the carbon is shifted to the oxygen and double bond is shifted over here. So we can have a structure CH3C. Since double bond is shifted, this will become single bond O, which is getting hydrogen from the carbon. Now this will become double bond CH2. Now if you look at this structure, I'm writing this a complete structure. Carbon is bonded to 3 hydrogen, then carbon O, H, double bond C, H and H. All single bonds are sigma bond. So we have 1, 2, 3, 4, 5, 6, 7 and 8. But in the double bond, there is 1 sigma and 1 pi bond. So 8 plus 1, that is total 9 sigma we have, 1 pi bond we have, and whenever there is an oxygen, it carries 2 lone pair. So we have 2 lone pair with us. Hence our option is D. Question number 4 is if Na plus is larger than Mg2 plus ion and S2 minus ion is larger than Cl minus ion, which of the following will be stable salt in water? Now if you combine this, we have 2 cations here and the 2 anions here. Let us talk about various combination. If the sodium combines with sulfur, sodium has 1 valency, sulfur has 2, we can get a compound Na2S. Then we can have a compound MgS, we can have a compound NaCl and we can have a compound MgCl2. In this case, we have to find which is the most stable salt in water. The most stable salt is the one which is water insoluble. So we have to find out of this which is water insoluble. For water insolubility, we have to see that stronger is the bond, it is least soluble. So in this case, to form a stronger bond, the sizes of the cations and anions has to be smaller and the charge has to be larger. Now in case of large charge, when I'm talking about it, Mg2 plus and S2 minus, they have the largest size charges in the cations and anions. So when they form a compound, that compound is comparatively stronger and this is stronger than the other. So it will be least soluble and the most stable salt in the water. Hence our option is option D, that's magnesium sulfide. Question number 5 is we have to find the electron deficient molecule in this following compound. When I talk about carbon, carbon is having 4 electron in the outermost shell, sharing 4 electron with the chlorine. So outermost shell of the carbon will be complete octet. In case of phosphorus, phosphorus contains, according to the atomic number 15, 5 electrons in the outermost shell, sharing 5 electrons with the chlorine, because there are 5 chlorine in the molecule, so it will be having 10 electron in the outermost shell. In case of boron, contains 3 electron in the outermost shell, plus it's sharing 3 electrons from the fluorine, so now it is having 6 electron in the outermost shell, so it is not a complete octet. Because of this, the electron deficient compound is option C. Question number 6 is the correct sequence of increasing covalent character in the following molecule. According to the increasing covalent character, according to Fajans rule, the lower the size of the cation, higher is the polarizing power and higher will be covalent character. Now if I talk about the 3 cations, we have Na+, we have Li+, and we have Be2+. In this case, there is larger size for Na+, then Li2+, and the smallest one is Be2+. As the Fajans rule says, smaller is the size of the cation, more is the polarizing power, and the higher is the covalent character. So highest covalent character will be with the beryllium and the lowest covalent character will be with the sodium, and hence our option is C. Question number 7 is we have to find the lattice energy of the alkali metal chlorides in the following compounds. Now we have a different compounds like this. In the group 1, first lithium comes, then the sodium, then potassium, then rubidium and cesium. As you go down the group, the size of the cation goes on increasing, bond becomes weaker, and the lattice energy also decreases. So lattice energy will be highest for the lithium and lowest for the cesium. Hence our option is option A. Question number 8 is the geometry of the electron pair around the iodine in IF7 we have to find. Now we have studied the formula to find Question number 23 is, in which of the following pairs both molecules possess the dipole moment, same dipole moment? If I talk about CO2, it's a linear molecule and SO2 is a bent. Since the structures are different, the dipole moment won't be same. BCl3 is a trigonal planar, while PCl3 is the molecule which is pyramidal in shape. Again, the shape is not same. In case of water, it's a bend shape, and SO2 is also bend shape. Since both have the same structure, the dipole moment will be same. Hence, our option is C. Question number 24 is, which of the following is having highest dipole moment? If you look at this structure, here we have a carbonyl group. Definitely it will create the polarity difference due to difference in electronegativity of carbon and oxygen. So this can be our option. Option B is also showing that two carbons are on one side and hydrogen on other side, creating the polarity difference. But in option C and D, we can see these are the trans molecule which are having the electronegativity groups on the opposite side. So their polarity is getting cancelled. So now we have to select between option A and B. But we can see there is more electronegativity between the C and O. Hence the highest dipole moment for the option A. Question number 25 is, the electronegativity difference between the nitrogen and fluorine is greater than that of between nitrogen and hydrogen. Yet the dipole moment of ammonia is 1.5, but it is larger than that of NF3. When I talk about nitrogen bonded to 3 hydrogen, it's ammonia, and nitrogen bonded to the fluorine, this is a structure. Now when I talk about the dipole moment, the bond dipole, the hydrogen and nitrogen, between the two, nitrogen is electronegative, so electron pull is towards the nitrogen, while the atomic dipole will be outside. So if I talk about the bond dipole and the atomic dipole, they are in same direction. While in case of fluorine, fluorine is more electronegative than the nitrogen, so the bond dipole will be towards the fluorine, while the atomic dipole will be exactly opposite to that. Because of this reason, there is some cancellation of the polarity in case of NF3, and its dipole moment is less than the ammonia. So our option is B. In ammonia, atomic dipole and the bond dipole are in same direction, while in NF3 they are in opposite direction. Question number 26 is, the hydrogen bond is the shortest in. We have the rule, stronger is the bond, shorter is the bond. Now out of these, if I talk, there is more electronegativity difference between the fluorine and hydrogen. Since this bond is stronger, it is a shorter bond. Therefore our option is E. Question number 27 is, what is the dominant intermolecular force or bond that must be overcome in the converting liquid methanol to a gas? When I'm talking about methanol, in which the hydrogen is attached to the oxygen, that creates more electronegativity difference. Therefore, between the two methanol molecules, the intermolecular force is hydrogen bonding. Question number 28 is, the energy gap between the valence and the conduction band for the diamond, silicon and germanium. When I'm talking about the conduction band and the valence band difference, more is the gap between the two, less is the conduction power of the particular element. Now out of diamond, silicon and germanium, diamond is a bad conductor of electricity, so we are expecting the gap has to be highest. Then silicon and the germanium will be lowest, because compared to silicon and germanium, germanium is a better conductor of electricity. Hence our option is A. Question number 29 is, which of the following molecule has the minimum bond length? We have to find. If I talk about the molecule O2, there are 8 plus 8, that is 16 electrons. If you write the electronic configuration, molecular orbital electronic configuration, so it is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2, 2, pi 2py2, pi star 2px1 and pi star 2py1. In all, if you'll find, in the case 2 plus 2 4 plus 2 6 plus 2 8 plus 2 10, so we have 10 bonding electrons minus antibonding 2 plus 2 4, 4 plus 2 6 divided by 2, so it's 4 divided by 2, that's equals to 2. When I talk about O2 plus, we have to remove one electron from this particular molecule. So when you remove one electron, the antibonding will be now equals to 5. So for O2 plus, it will be 10 minus 5 divided by 2. So it's 5 divided by 2, it will be 2.5. In case of O2 minus, since you are increasing one electron, it will be increased in the antibonding orbital. So now antibonding electrons will be 7. So it's 10 minus 7 divided by 2. So 3 divided by 2, that will be equals to 1.5. And final, for O2 minus, we have to increase one more antibonding electron. So 10 minus 8 divided by 2, that will be 1. So the highest bond order we can see for the 2.5, that is O2 2 plus. Higher is the bond order, shorter is the bond length. Hence, our option is B. Question number 30 is, when O2 is converted to O2 plus, what will happen? O2 is a paramagnetic molecule having its last electron in the antibonding orbitals. When you are having O2 plus, that means you are removing one electron, and as you will remove one electron, the paramagnetic character will decrease, because oxygen is paramagnetic due to 2 unpaired electrons, and since it has 2 unpaired electrons, when I'm removing one electron from this, now O2 plus will be with one electron only, that is unpaired. So hence the paramagnetic character will decrease, but at the same time, since you're increasing, or the bond angle of that particular molecule will be increasing. Hence our option is D. Question number 31 is, which of the following represents the arrangement in increasing order of the bond order and the bond dissociation energy? In the previous question number 29, we calculated for the same molecule, where for O2 the bond order is 2, for O2 plus it's 2.5, O2 minus it's 1.5, and O2 2 minus is 1. So highest bond order is with the O2 plus molecule, and the lowest is with the O2 2 minus molecule. In between you can find there is O2 molecule, and O2 minus will be around 1.5. Hence our option is option B for the question number 31. Next, question number 32 is bond order for the CO molecule we have to calculate. Now carbon contains 6 electron plus 8 oxygen from the 8 electron from the oxygen, that will make 14 electron. So if we write the electronic configuration for this, it is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2, sigma 2pz2. So when I will calculate the bond order, there are 10 bonding electron minus 4 antibonding divided by 2, that will be equals to 3. Hence our option is C. Question number 33 is, in the charge of the NO plus to NO, the electrons added 2. When I talk about NO plus, electronic configuration is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2, and sigma 2pz2. When I'm talking about the molecule NO, you're adding one electron over here. Since all the orbitals of NO plus are completely filled, now the next electron will be going to the pi star 2px. And since it is going in pi star, our option is D. Question number 34 is the molecular orbital electronic configuration for the X anion is kk dash sigma 2s2 sigma star 2s2 pi 2px2 pi 2py2 sigma 2pz2 and pi star 2px1. If you will calculate this, kk star, that is first shell containing 4 electrons, total there are 15 electrons. And since there are 15 electrons, if I talk about the nitrogen, each atom is 7, so N2 will be 7 plus 7, 14, and if you add electron to that, it will become 15, so it should be N2 minus species. Hence our option is